Zinc is a trace mineral with outsized importance in cellular maintenance, particularly in the context of immune regulation, antioxidant defense, and enzymatic function. But one of its most underappreciated roles lies in its support for autophagy, especially at the lysosomal stage. While much attention in autophagy research focuses on the signaling pathways that trigger it, such as AMPK activation or mTOR inhibition, equally vital is the process's final stage, lysosomal fusion and degradation. Zinc is essential for the proper functioning of lysosomes, the cell's degradative organelles, and it contributes directly to the acidification and enzyme activity needed to break down damaged cellular components. Without sufficient zinc, autophagy may be initiated, but it stalls during execution, leading to incomplete clearance of waste and impaired cellular renewal. Zinc supports multiple stages of the autophagic pathway. It aids in the formation of autophagosomes, the vesicles that engulf damaged proteins, organelles, or pathogens. More importantly, it is critical for lysosomal acidification, a low pH environment that activates catabolic enzymes responsible for digesting cellular debris. This acidification process relies on proton pumps and membrane integrity, both of which are stabilized by zinc's presence. In zinc-deficient states, lysosomes can become dysfunctional, resulting in poor turnover of cellular waste, buildup of oxidative byproducts, and an increased burden on the endoplasmic reticulum and mitochondria. This dysfunction not only impairs autophagic flux, but also promotes inflammatory signaling, contributing to chronic cellular stress. Zinc also interacts with important autophagy-regulating proteins, including those associated with stress responses and metal-sensing transcription factors, such as MTF1. Additionally, it helps maintain the structure and function of membrane proteins involved in vesicle trafficking and fusion events. This makes zinc a structural as well as functional contributor to autophagic success. Importantly, zinc also serves a dual antioxidant and anti-inflammatory role by supporting the activity of enzymes like superoxide dismutase, SOD, which detoxify free radicals that would otherwise damage cellular components and overwhelm the autophagy system. In neurons, immune cells, and epithelial tissue, zinc's contribution to both the initiation and completion of autophagy helps maintain cellular cleanliness, repair capacity, and resilience under stress. From a nutritional standpoint, zinc is widely available in both animal and plant-based sources, though its bioavailability can vary. Oysters and shellfish remain the richest sources, offering a highly absorbable form of zinc that supports immune and cellular repair processes. Red meat, poultry, and liver also provide substantial amounts. For plant-based diets, legumes such as lentils and chickpeas, as well as seeds like pumpkin, hemp, and sesame, are important contributors. However, phytates in plant foods can bind zinc and reduce its absorption, making soaking, sprouting, or fermenting strategies useful for enhancing bioavailability. Zinc supplementation can be considered for individuals at risk of deficiency, particularly vegetarians, older adults, or those with chronic illness or digestive disorders that impair mineral absorption. Zinc picolinate, gluconate, or citrate forms are commonly used for their higher absorption rates. Zinc's effect on autophagy is not isolated. It works in close partnership with other micronutrients that support lysosomal integrity and cellular recycling, including vitamin A, selenium, and magnesium. When viewed through the lens of holistic cellular care, zinc emerges not only as a mineral for immunity or wound healing, but as a key enabler of the cell's ability to break down, rebuild, and adapt. Ensuring adequate zinc intake helps keep the final phase of autophagy, degradation, and recycling running efficiently, making room for regeneration and reducing the burden of cellular aging. In this way, zinc plays a subtle but powerful role in the long arc of health, contributing to both daily maintenance and long-term resilience through its unique support of autophagic lysosomal function.